Did they even have to? I assume so.
Good? Excellent. Good morning, everybody. How are you all doing today? Not bad, yeah? Still the first week, nothing's really become difficult yet, so, yeah. So it goes. I don't think we have any extra announcements or anything like that to talk about today, so we might as well get straight into business, shall we? Good. As opposed to yesterday, which was all, or yesterday? Whenever we had class. Anyway, so, last time, we primarily went over the course syllabus. Unfortunately, I forgot my camera, so we were not able to record that session. And in contrast to my first year class, where I actually, recorded an extra video and put it up for them, I figured that by second year, you guys should be able to read syllabus. So if you missed last class and you didn't understand or get my going through of the syllabus, you can easily obtain the same information by simply reading it yourself, so I would encourage you to do so. Aside from that, we got slightly into our first topic, wherein we shall introduce the concept of both the C programming language and various bits and bobs related to low-level language development. So, pretty much every one of you should know Python from first year, correct? What are some other languages in the room that you guys know? Yeah? JavaScript. Java, okay. C# maybe? Ooh, now that's getting a little bit more into the actual thing that we're actually going to be doing. Yes? PHP? Cool. Anything else? Any other languages in the room? So, more or less every single language that anybody mentioned during that little interlude is a C-based language. So, the C programming language, which was developed in the late 60s, early 70s, was so widely influential on the development of further programming languages that it's kind of like studying C, like the equivalent in other disciplines would be something like studying Latin, where, many European languages are Latinate and have, Latin roots, so studying Latin allows you to understand many words in many languages. This is kind of the same effect by studying the C programming language, except whereas Latin is a dead language, which nobody speaks anymore, C is still an actively developed programming language, despite the fact that it is 50-odd years old. Actually, I think exactly 50, probably not exactly 50 years old. But anyway, so the question that might remain, given that there have been a cornucopia of languages that have been developed using C as its base semantics, why is it that none of these languages has managed to unseat C from the throne that it currently occupies inside of the software ecosystem? Well, basically, C is one of the lowest level languages that exist. It's like literally one step above assembly language. And assembly language, as we're going to find out in this course, is it's hell by way of tedium. It is the worst language conceivable, with the possible exception of FPGA languages, which are not properly software languages, which you'll all learn in due course when you get to 3TB4. C is such a very low-level language it gives you direct access to many of the CPU's native functions, which other languages attempt to hide from you because they are difficult to work with and understand. However, by understanding what is difficult to understand, you tap into the full potential of the processor that you're working with. You can optimize things in C to a degree that is not possible in higher level languages. C, despite being one of the older languages, possibly one of the oldest languages at this point, if you don't count things like COBOL, is still the fastest compiled language. It's above assembly language, right? So, why would you need a fast language? I mean, aside from the obvious reason which it makes things faster. Like, where do you need fast code? Frequently executed kernel operations. So, are you guys know what the kernel is? Thumbs up, thumbs down, a little bit? Yeah, okay. So, this is the structure of your operating system, all right? So, if you imagine your operating system as a sequence of concentric circles, the outermost layer is your solitaire program, or your Word application, or your browser, that what we call user-level code, right? So, we'll call this the user level. Between the next layer down, you have an API that accesses operating system functions and commands, right? So, underneath the user level, you have the OS level. So what's underneath the operating system? The kernel. The kernel is composed of that code which interfaces the operating system with the hardware itself, right? So we then have kernel, and then we have the actual hardware. Wow, that's a... my goodness. So, basically, the lower down you get, the more frequently these commands are executed, right? Kernel code is stuff like, video display drivers is a good example. How frequently does your monitor have to be updated with a new image? Well, it depends on the frame rate of your monitor, right? Yeah, let's say it's 60 FPS, because 30 is for people who don't know true gaming. Or, cinematic games, so to speak. So, how many pixels are there in a 1080p display, right? Does anybody actually know that? Yeah.
I think it's like 3.8 million.
Yeah, so 3.8 million. Even if you're wrong, let's say you're right. So 3.8 million pixels. Each one of those pixels has to be processed by the CPU, right, to determine what the color is supposed to be. If it's a complicated operating system with like transparency layers, then you have to calculate the pixel values being sent by multiple windows, right? And it's all got to be processed 60 times per second, right? That code is frequently repeated and has to be fast. Otherwise, you end up with, lower frame rates than you would want in your game. And of course, it doesn't have to be video games, of course, but video games are a good example. If it's a video game, then you not only have to, process colors that are being sent by multiple windows altogether, you also have to trace geometry inside of three-dimensional geometric environments and determine pixel values that way. And, there's a reason that we use GPUs to accelerate this type of thing. But the GPU isn't the code, right? It's hardware. It doesn't matter how good your processor is, if the code is inefficient, then the whole system is inefficient, right? I'm teaching algorithms course at the moment as well, and one of the slides in that algorithms course claims, and it's a true claim, hardware acceleration might be able to get you 10 to 100 times speed increase, but an algorithmic adjustment can literally get you millions of times speed increases. And we'll talk about those types of things as we get into programming in this course, but anyway, so why use a low-level language? Low-level languages use a small number of hardware instructions per operation, so programs written for low-level languages can be very small and run very quickly relative to high-level languages. Some optimizations are not even possible in high-level languages. Some non-traditional programming environments, such as microcontrollers, do not even support high-level languages, because why would you? So all of you are mechatronics students, which means that you must think of programs as not just existing inside of what are properly thought of as computers. You must also attend to the domain of the embedded system. Can anybody tell me what an embedded system is? Oh, come on, you guys chose mechatronics and nobody can tell me what an embedded system is? Yeah.
It's like, oh my god. It's a system that uses hardware, software, and electrical parts all working together to perform like a specific I guess function.
Sure, that's an okay definition. Anybody else? So, at the back there.
You actually told me this last week.
Yes. Yeah, I did. You remember?
Yeah. So when you got a physical device, you
Yeah.
got a system with the software that makes the device work.
Yes. So in general, what you're targeting are physical devices that have embedded controllers, right? Embedded controllers are processors. So it's everything, technically speaking, these guys are considered embedded systems because of the architecture that they run. But it's everything from a cell phone all the way down to a kitchen timer, right? Any degree of processing or electronic trickery it doesn't even necessarily have to have a processor per se to be an embedded system. You can have these calculations occur in pure hardware with no ability to program them whatsoever. But this is the domain, hypothetically speaking, that this degree program is preparing you to work in the embedded systems domain. It's more difficult to program embedded systems than it is to program a regular computer because you don't have the same kinds of bells and whistles available to you that your software engineering brethren will delight and astound you with over the coming years. So when you are making an embedded system, a lot of the time you are making a product, right? The costs that go into a piece of electronics include things like how much memory you give it, right? How much memory do you think a kitchen timer requires? Not all that much, right? Enough to store a counter and enough, you need some circuits to interpret a counter. You need to be able to start and stop at the counter, and that's pretty much everything for a kitchen timer, right? So programs themselves occupy memory, obviously, right? The larger the program is, the more memory it requires in the device in which it exists. So, to program in a higher level language produces many, in some cases orders of magnitude, more instructions that compose the program than it would be the case if you implemented it in C. Interpreted languages are particularly bad for this because, things like Python and Java, Python requires more or less the Python interpreter to be running in order to execute a Python program, right? You guys know about interpreters versus compilers? No, not really? Oh boy, we're gonna have fun in this class then. So, they taught you Python, and they didn't even tell you what an interpreter is. I'm shocked. I'm appalled. So basically, programming languages come in two varieties, and I know I'm like a long way from the slides at this point, but just go with it. You'll get used to it. This is just the way I do. Don't worry, hopefully at some point we'll learn something useful. So programming languages in general come in two distinct varieties, right? You have compiled languages, of which C is an excellent example, and you have interpreted languages. So a compiled language takes source code and all at one time compiles that source code to object code or machine code, that which is directly executable by the processor. Interpreted languages, on the other hand, are not compiled directly to machine code. What happens is you start up the interpreter process. The interpreter process feeds the program in Python's case, one line at a time, into the interpreter. The interpreter compiles, essentially it compiles the program at runtime instead of before runtime, right? In C, the process, and we're going to see this, but if I stop every time I use the word C in this C class, thinking it's a pun, we'll never get anywhere. So I'm just going to ignore that from now, I hope. But anyway, so what Python does is you sort of have this fat, bloated bloatware of the Python interpreter sitting on top of your processor, consuming all of these cycles, doing all of its dynamic type checking that it's so proud of, despite the fact that it's garbage. And so it's sitting on there, and it has to be running, and you have to feed the lines in one at a time. That's why Python programs are called Python scripts. They're not programs, they're scripts. So, take that to an embedded system context, right? You would have to have an embedded system that was running the Python interpreter to be able to program an embedded system with Python. Given that the Python interpreter is a ridiculous conglomeration of dynamic type checking and bloatware, you would vastly increase the price of the embedded system that you were designing for in order to accommodate software that you don't need because you can just program in C, right? So learn C programming because that's the language of the domain that you're in. Does that make sense? Any questions about any of that? Did you learn anything yet? Hopefully? Don't worry, not every little thing I say is going to be on the test. Primarily, you'll be tested on how you program C. So learn how to program C, and that'll be good. So, good. So, I've talked about this, I've sort of brushed against this, but let's actually examine how it is that a CPU works in broad terms. This is what's known as the von Neumann architecture. That's pronounced Neumann, even though it's like Jerry Newman, it's Neumann. Anyway, that's a Seinfeld reference if you're all too young for that. It's on Netflix, go watch it, it's a funny show. Anyway, you have to do homework though. I digress. So you have the central processing unit, right? The CPU. In general, the CPU is composed of a control unit and an arithmetic logic unit. This guy, the ALU, contains the actual circuitry that performs operations like addition and subtraction and Boolean comparison, etc., etc. The control unit controls what data is put into the ALU and when, and where it's sent afterwards. So between the two of those, that's sufficient to be able to grab memory from places and put it back and process it, which is everything that you need in a CPU. So the CPU itself communicates with a memory unit. And the memory unit might be many different types of memory. It might be, RAM chips, it might be your hard drive, it might be inbuilt CPU register memory, which is something you will definitely learn about over the coming years. But anyway, it interacts with memory. The CPU itself doesn't store information, except in a very meager fashion. When you take 2TA4, you will learn about these guys, the ARM processors that go into your cell phones. These CPUs only have the ability to store 16 32-bit registers. And that's all the memory that the CPU has available to it. So, if you want any more memory than that, you have to interact with external memory, like RAM or ROM or whatever it is that you want. In addition to this picture, we also have input devices and output devices. In the kitchen timer example, obviously the little LCD display with the number, that's your output. The buttons that start and stop the timer, those would be the inputs. Things get more complicated than that, of course, but that's good enough to illustrate the idea. Any questions about this? This should be like roughly, you guys should know this pretty well already, but So, memory then. Computer memory can be stored in many ways. You have read-only memory, which is your system's permanent data storage. Your file system is stored on either solid-state drives or hard drives. These are ROM. This can also be flash memory, as in USB drives. Often, if you're on an embedded systems application, you're talking about flash memory. You might even be talking about, more exotic flavors. But ROM, generally speaking, is the permanent memory. What makes it permanent is that when the device powers down, this memory retains its values. In contrast to permanent memory, we have volatile memory, or random access memory. The thing that makes it volatile is that the values in this memory do not survive a power down cycle, right? The memory is wiped when it isn't being provided electricity. On execution, programs are loaded from ROM into RAM. So one might ask the question, if ROM is permanent and RAM is not permanent, why would anybody ever use RAM? Why wouldn't you just use ROM for everything? Because it's permanent. Yes?
Isn't RAM a lot quicker to access and process by hardware?
Yes. So basically, your main engineering trade-off when it comes to memory is that speed of access is inversely related to the permanency of the memory unit. And you actually have a wide variety of different types of computer memory, which have various access speeds versus permanence. Pardon me. To take the example of a hard drive in the traditional sense, do you guys know how a hard drive works? Yes? No? Maybe? Okay. So, a traditional hard drive is a derivation of the same type of technology that makes a cassette tape work. Do you guys know what cassette tapes are? Hopefully. Okay. At some point I'm going to ask that question and nobody's going to know what a cassette tape is. But anyway, so it's magnetic memory, right? You have a disk, you have a read head, right? This read head finds a position on this circular magnetic disk, and it can either read or write a 1 or a 0, right? the magnetic polarity of the pieces that compose the disk is configurable by applying magnetism and can be read using other, electrical means. So this means that, roughly speaking, unless you've got like one of these fancy layered hard drives, which have, you can store like, maybe 8, do 8 bits at a time or something like that. The read speed of a hard drive of this manner is pretty limited. You can only do 1 bit at a time through the read head. Now, you can do it pretty quickly, right, because technology is pretty good, but, it's a very narrow channel that the data is coming through. Other types of memory are much, much quicker because you can have, basically this large matrix of individual electronic memory cells, which are solid state, and you read them all in a group, and you don't have to go through them, one thing at a time. So, but a lot of the time this means that you have to maintain power to the system, right? But anyway, the most volatile memory are the registers which are contained in the CPU itself. So these, fortunately, are the most frequently updated. But the thing, so what makes volatile? One of the things that makes volatile memory volatile is the fact that, depending on the technology, the bits can get randomly flipped if they aren't updated, like if they aren't refreshed often enough, right? So that, basically your very, very high-speed applications where things are being updated and refreshed very frequently, you don't have to worry so much about bit decay, is what it's called. But, it's still a thing that happens, Honestly, it's a miracle that anything works. So, anyway. So, the data that we access from a memory system can be categorized hierarchically. The smallest individual atomic unit of memory is, of course, the bit. Bits are organized into bytes. Bytes are organized into words. Right? The definition of a word depends on the system in which it resides. Generally speaking, the CPU and the number of bits that it can process, or the number of bytes that it can process, in a single step determines the word size of the machine. So, for example, the Nintendo Entertainment System was an 8-bit machine. So, it was restricted to displaying, for example, 256 colors, because 256 is 2 to the power of 8. That's the number of individual numbers that can be represented in, using an 8-bit number, right? So, they did pretty well with the NES. But, a lot of the games were like some of the first really, truly playable games in video game history. And if you don't believe me, go and play some Atari games. Holy smoke. Like, there's maybe like 2 good Atari games, honestly. But anyway, by the time we get to the Nintendo 64, the reason that it's called the Nintendo 64, is that it's a 64-bit machine. So, you can do all kinds of interesting things like support floating point math. You guys know floating point, or have heard of it, I assume, right? Good. Yeah, if you take a look at a lot of the old NES games, there's like very little evidence whatsoever that floating point operations are even occurring. So yes, because obviously to generate a 3-dimensional space, you need the ability to have floating point numbers. So that was a precondition to the N64 being the first 3-dimensional Nintendo platform. They kind of got away with it with the Star Fox games, but come on, have you seen the frame rate on those things? Go watch a video. It's terrible. Anyway, so skip that. I don't really think that's important. So words. The word is the largest amount of memory that can be processed by the CPU in a single step. In general, we take memory and we organize it into characters, characters into files, and files into file systems. I'm going to just skip these slides because I don't like them. There we go. So let's talk about the C programming language itself. C evolved from two previous languages, BCPL and B. So C is the successor to B, which may have been the successor to A. I'm not sure. It's possible. BCPL, or the Basic Combined Programming Language, was developed in 1967 by Martin Richards as a language for writing operating system software and compilers. This period from the late 60s to the early 70s is it is a time of critical importance in the history of computing. Basically what you have, it's like the Cambrian explosion but with compilers. The idea that you might write an operating system and have, programs running all the time and stuff like that, this is a new concept in the late 60s. Prior to this, everything's done on punch cards, and basically your program runs on the bare wire of the central processing unit itself, right? The thing that makes this possible, more or less, is miniaturization, right? So I think this is like my own personal conceit with respect to the discipline that I'm in, but I think that if you took all of the inventions of the 20th century and you tallied up their impact on human society, the single greatest invention of the 20th century is the solid state electronics. And I'm including in that the atomic bomb and nuclear energy and all of that stuff. They had the early prototypes of solid state electronics in the mid to late 40s. By the time you get to the 60s, solid state electronics have miniaturized to the point where they have now completely outcompeted older modes of computation, including vacuum tubes and relays and all of these sort of various electronic gadgetry. In the old days, if you wanted to flip a switch, you needed to generate magnetism. But after the development of solid-state electronics, all you needed to do was to be able to produce a very, very small piece of silicon to affect the same thing. So the miniaturization in the 60s catches up to where computers were. You then, just a few short years after that, have the explosion of the personal computer market, because computers are now miniaturizable to the point where they can fit on a desk, which was something completely inconceivable merely 10 years before that, right? So, we start to have the luxury of saying, hey, we have these things, maybe we could try to make them slightly less of a pain to work with. So, the first step in that was to find a better way to program them. Hence the development of programming languages and compilers in the sense that we now know them, right? So anyway, compiled languages were, C was certainly not the first compiled language, but it was definitely the first one that really took off. It's like, how on Steam you have all of these indie games and one or two of them rises through the muck to become popular. This is kind of what happened with C. So anyway, Ken Thompson modeled many features of his B language after their counterparts in BCPL, and in 1970 he used B to create early versions of the Unix operating system at Bell Laboratories, which is kind of that Bell Laboratories in the late 60s, early 70s is it's the womb in which the modern era was formed. So, the C language was evolved from B by a man by the name of Dennis Ritchie at Bell Laboratories and was originally implemented in 1972. Which would mean that this year it became 50 years old. C initially became widely known as the development language of the Unix operating system. Unix is extremely important historically. For a long time, it was really the only operating system that was worth anything. They did a clever thing. This was back in the days when software was not so freely distributed. Basically, at Bell Laboratories, they developed Unix, and they they leased it to universities for very, very, very little money relative to the amount of money that you usually charge for pieces of software in those days. Because they gave Unix to the universities, all of the university students learned Unix. All of the university students learned C. And because they learned Unix and C, that preference was held as they entered industry and developed their own things. So, very cleverly, Unix used basically a good licensing deal to become the most popular operating system. At a certain point, they fumbled it, though. The company, the lab or the company was acquired. I think the lab was acquired by Oracle or something, and they decided to start charging for Unix. And that led all of these very clever developers to say, you know what, I'm just going to write my own operating system then, screw you. So they did. And that's how you get, OpenBSD and Linux and all of these Unix-derived systems. If they hadn't tried to charge money for Unix, everybody would still be using Unix. Incidentally, Windows is terrible, and it does stuff just to be different. You know how when you do file directories in Windows, the slash goes it's like a, whatever the slash is, that's, I forget if it's backslash or forward slash, but it's the opposite of Linux, Unix, Mac, all sane operating systems. And the only reason they did that was to be different from all the rest of them when they wrote MS-DOS. Ugh. Bill Gates was a much better businessman than a programmer. But anyway, so many of today's leading operating systems are written in C or C++. C++ is kind of an interesting one. It took a lot longer to develop than C because it's a lot more complicated. But basically, as soon as C really started to take off, people started complaining that it didn't have language features because it's a very simple language. And so C++ was developed to sort of, it was like one of the first add-on packs, right? So it adds all of these features in which are, prominent in were prominent in other languages at the time. But, so when you talk about C, you often say C/C++. You'll see that a lot. That's because C++ uses C as its base language. All C programs are valid C++ programs, as I said yesterday, or the day before. But anyway, one of the great advantages of C versus all of its competitors at the time was that it had a very strict regimen of standardization. So this is the way that software used to work, right? You would have a company that wrote a specification for a program, and then you would have other companies make their own implementations of it. You can still see this in languages like SQL. There are many, many different types of SQL database, but there's one SQL language. So this was how it worked a lot of the time. And companies would charge for their specific software, but they themselves would be charged for using the standard, right? So this was the same way that C worked, except that where a lot of standards would leave a lot of wiggle room to the individual companies producing the implementation to sort of add their own features in and stuff like that, the C standard was very strict and made it so that most of the time a C program written for one compiler would work on everybody else's compiler, right? And not only that, it basically meant that in order for a C program to work on any architecture, all you had to do was have a C compiler for that architecture and some way of getting the program into it, you know. So, C was able to achieve a universality never before known in computing, right? Prior to the existence of C, if you had two different computers with two different architectures, you probably had to write a program twice, once for each architecture. Because different architectures would have different compilers bundled by the manufacturer, and the different language features would be, like the language feature sets of these two languages would be sufficiently far apart that a language, like a program for computer A would not necessarily compile on computer B, right? C comes along, you can just throw it at both of them, and as long as it has a C compiler, it just works, right? This also contributes to C's just explosion as a language in the early 70s. And was very influential on the idea of, for example, the Java virtual machine, right? Anyway. So, applications of C. Because of its high performance characteristics, C is still used a lot, despite being 50 years old. Portability across hardware, many hardware implementations and overall performance led C to be an operating systems development language, primarily. Linux, portions of Windows, and the Android operating system all use C. Apple's OS X uses Objective-C, which is basically Apple's version of C++. You know, classes, object-oriented, you know, you've got objects in C++, you've got objects in Objective-C. It's called Objective-C because it's C with objects. In embedded systems, C is one of the most popular languages of development, and because embedded systems are typically highly memory conservative, right? You might be working with memory in the, like, if you're working with an amount of memory in the kilobytes, you're working on a relatively large system. So, real-time systems. In mission-critical pieces of software, like, for example, pieces of code in airplanes, right? How much flying does the pilot do versus the electronics these days, right? If that software goes down irrecoverably, you might have big problems, right? And that's only one example, right? Code inside of nuclear power plants, right? High performance characteristics dramatically increase the feasibility of meeting timing constraints. If you need your software to react in X number of milliseconds, like for example, if your reactor is going into meltdown, you don't want that thing running frigging Python, right? In addition, communication systems is a pretty big application for C. Massive quantities of data being routed around, optimization becomes crucial. Does anybody know what the primary expense of running a server farm is? Anybody take a guess? You at the back, sir. Well, yes, but, okay. But of the things you do with electricity, what's the biggest thing? Air conditioning. Yeah. Heat dissipation is a huge problem in these big server farms. Like, you guys know about SharpNet? On the supercomputer we have on campus? Oh my God, that's gotta be wrong.
Oh yeah.
Okay, yeah, all right, thank you, sorry. So SharpNet is the McMaster's supercomputer, right? If you look in there, you'll see these big racks of servers, and you will see one hell of an HVAC system, right? Every command that gets executed by a CPU produces a tiny little amount of heat as dissipation. You know, it's electronics heat up as they work. That's just how it works. The fewer commands you're executing, the less heat you're generating. The more efficient your program is, the less air conditioning you have to pay for. It's kind of interesting. They're like putting server farms like underground now, because it's like it's. If you go down into the earth like only a few feet, it starts to be like a consistent 10 degrees Celsius. So you know, like old bomb shelters and stuff, they're starting to look like throw servers in them because it's easier to keep them cool down there. But anyway, so I haven't updated this in a little bit, but this is the Tyobi Programming Community Index. Basically, this is a measure of the popularity of various programming languages. This is measured by how frequently people search how to program them, right? So it's perhaps also a good measure of which programming languages are being taught in courses and how much confusion people have about the programs that are being taught in courses. So it's not a pure, like this isn't necessarily a pure index of how much industry goes on with things, but if you take a look, C is this light blue line, always a very popular language except for this inexplicable dip around 2017, right back up again. Currently the most searched language, C. I think it still is. This black one is Java. Python is this green one. You can see it's become more popular recently, but historically speaking, it's not necessarily a first-class language. C++ has gradually declined over the years. C# sort of peaked around 2011. Visual Basic peaked, you know, in sort of the mid to late thousands and is now, you know, not used much at all. But yeah, so C is one of the big guys. Yeah? Any questions? Cool. Now we got 2 minutes. I kind of already talked about this, but one more slide, then you can go. Okay? The semantics of the C language are set by the International Standards Organization, ISO, and the International Electrotechnical Commission. These are bodies which you will come to be familiar with in your practice as engineers. So C18 is the most recent version of the C standard. As of the creation of the slides, which was only a couple of years ago, there are only 3 C compilers which are compliant with the specification. GCC is the one that we will consider the standard compiler for this class. This is the GNU compiler collection. It is the standard compiler used in Unix and Linux operating systems. This is actually a very important thing to note, so if you could please pay attention to this. Clang is different from GCC. Despite the 2 compilers, roughly speaking, accepting the same languages, there are slight differences. Some things which are errors in Clang are warnings in GCC and vice versa. So a program written for GCC will not necessarily compile under Clang. Why is this important? If you're on a Mac, it comes natively installed with Clang, and if you ask for GCC, it redirects you to Clang. So, if you're on a Mac, install GCC. Make sure that the compiler that you're using is the standard compiler for this class, because if you submit your assignment and it doesn't compile when we go to grade it, it's not going to be worth much. And, you know, lots and lots of students get caught on this. And incidentally, the Windows C compiler, which is called the Windows C compiler, is that on this list? No, it's not even it's not even compliant with the C specification. So, do we assume that anything that will compile under the Windows C compiler, which by the way is the one that VS Code uses natively, do we assume that those will compile under GCC? No. Capici? All right, get out of here.
Yeah, but
I guess too.